First of all, I'd like to thank my nominators and the awards committee for this award. I'm both honored and humbled knowing how important many of you have been in any success that I've achieved over the years. This award is truly the highlight of my career, so thank you. This presentation is going to be a little different than past Award of Excellence presentations. As most of you know, for some time I've been battling ALS, so you'll have to bear with me if my voice falters a little bit. Also, I wanted to thank you all for your support of the Rhode Island ALS Society as part of the NAB's Fun Run and Volleyball Tournament. I know how important these regional ALS societies are in helping people with this disease cope. So thank you very much. That was a really nice gesture. So in this talk, I want to highlight collaborative research that I've been involved with over the years, both to give credit where it's due and because this has really been the most exciting type of research that I've been involved in over the years. And as my title suggests, I think I've often just been riding the coattails of others. So I began as an engineer, but very soon found out that what I really wanted to do was ecology. And of course, as all you know, that's where the big money is. My PhD advisor at UNC, the late Dr. Edward Kensler, gave me the opportunity to be involved in a very interesting project studying swamp streams in eastern North Carolina. We published several papers, including one in limnology and oceanography in the upper left column, or upper left part of the slide. In that paper, we showed that streams draining wetlands exported much higher DOC than streams without wetlands in their drainage. The bulk of my dissertation was published in an ecological monographs paper showing that streams with seasonally inundated floodplain wetlands have very high rates of nutrient retention and carbon processing. Back in the 1970s, stream channelization was occurring very rapidly, and this involved draining of the floodplain swamps bordering these streams. And I think the real value of this work was to show how important streams with intact floodplain wetlands were for retaining nutrients from agriculture and preventing their loss to coastal estuaries and the ocean downstream. So I arrived in Oak Ridge in the fall of 1979 and soon got involved in a new project known as stream nutrient spiraling. And the project was being led by some impressive guys whose names you probably recognize, although I suspect you don't recognize them in these photos. We did lots of field and laboratory experiments, dumping radioactive phosphate into streams in the early 1980s. Incidentally, I don't think that even we could get permission to do these kind of field radiotracer releases today. We showed in one of our papers that there were large seasonal variations in the uptake length of phosphate, resulting primarily from large seasonal variations in the abundance of decomposing leaves. This suggested that microbial uptake during leaf decomposition was an important regulator of nutrient uptake in streams. We used laboratory stream experiments shown, an example shown here at the bottom of the slide, to examine relationships between nutrient uptake and various stream characteristics. And one of these experiments We varied detritivore density and found that the higher densities of detritivores reduced nutrient uptake rates by increasing the rate of leaf decomposition, leading to lower microbial biomass as the experiment progressed. In the early 1990s, I was very fortunate that Amy Roseman decided to do her doctoral research in Walker Branch, examining controls on stream periphyton. Amy published a number of papers on her work, including a paper in ecology that's been cited over 200 times now. Amy did a series of factorial experiments in streamside channels, manipulating light, nutrient concentrations, and herbivore densities. She found that periphyton were controlled by both bottom-up, primarily light and nutrients, and top-down factors, primarily herbivory, and that these factors varied seasonally in their importance. In another paper based on her work, Amy showed that the proximate controlling factor was not necessarily the factor that ultimately controlled periphyton growth and prevented large growth rates, and that the proximate and ultimate controlling factors varied seasonally. About the same time, Al Steinman accepted a postdoc position working with us on a project studying the role of periphyton in nutrient cycling and stability. In addition to doing some great work and publishing some outstanding papers, Al benefited from an exposure to a more laid-back Southern approach to life and work. Most of you probably don't know, but Al was quite a hard-driving guy in his early years, and we'll take some of the credit for turning him into such a easygoing, warm fellow that he is today. In a study published in Ecology, we showed that in well-developed periphyton communities, internal cycling satisfied a large fraction of the nutrient demand, but high rates of grazing limited biomass development and internal nutrient cycling. In another study, Al showed that resistance and resilience of periphyton to disturbance was increased by nutrient input, but reduced by high rates of grazing. Also in the early 1990s, Dave Genero, an MIT doctoral student, came to Oak Ridge to do his research on catchment hydrology and flow path dynamics. This was very fortunate for me, since I really didn't know anything about hydrology, and Dave has taught me a lot. In several studies using natural tracers and end-member mixing approach, we found that there were 3 important chemically distinct flow paths generating stream flow in Walker Branch, and that these 3 flow paths varied greatly under different hydrologic conditions. We found that this variation in the importance of different flow paths explained a good deal of the variation in stream water chemistry. For example, the surface flow path, which was primarily dominating during storms, delivered water to the stream of very low nutrient concentrations, whereas the deep flow paths that interacted with the bedrock at depth delivered water that had somewhat higher nutrient concentrations to the stream. And this deep flow path was primarily important during base flow. Well, Eric Marzoff joined our group about 1992, and he and Al Steinman modified a field technique that had been developed long ago by Howard Odom for measuring stream metabolism at the scale of entire stream reaches. These modifications included high-frequency measurements of dissolved oxygen and temperature, and in situ salt and propane injections to directly measure oxygen exchange between the water and the atmosphere. This technique is now being used quite widely in streams.